In the name of God, the compassionate, the merciful, engineering plasticity, chapter 5, elastic plastic analysis of bending. Part 1. What you are going to learn in this chapter is you will be able to answer these questions after the chapter is finished, hopefully. What are the basics in the bending of beams? What is an anticlastic curvature? How do we analyze the elastic bending of beams? How do we analyze the incipient yielding in bending? How do we proceed to analyze the elastic plastic bending? How do we analyze the plastic behavior under bending? What is the collapse load? And what is plastic hinge? Now, if you remember from your strength of material in your BSc course, when we have a beam like this and we put bending moments, pure bending moments, like that, we get a curvature in the beam as shown in here. This R is the radius of curvature of the beam. This line shown here, the dashed line, in fact is a plane perpendicular to the display that you are seeing now. This is a plane, and this plane we say that is a neutral plane, and its length doesn't change, it doesn't elongate, and it doesn't compress. So the length does not shorten or lengthen. But this line over here, or this plane over here, you can see that relative to this line, it has elongated, and this line relative to that line, it has shortened. So clearly this must have elongated, so it's under tensile load. This has been shortened, so it must have been under compressive load. We call this line, when we have a look at the beam, we say that it's a fiber, okay? It's just a fiber on top of the beam, and it's a fiber on the bottom of the beam. So when the bending moment is in this direction, we get this kind of curvature, and these fibers under compression, and these fibers under tension. Now if we look at it from the side view, from right hand side, if we have a look at the cross section of the beam, if the original cross section was a rectangular shape like this, B times H is the cross section. After bending, it becomes like that. Okay, so if the curvature here on the bottom is in compression and this one is in tension, then when you look at it from the right hand side, from this side, when you look at it from this side, okay, like that, that is the cross section. That's the original cross section before bending, that's after bending. So you can see here that the curvature is different. It's completely opposite to what we have here. Completely opposite to what we have here. So the curvature on the top is under compression, and on the bottom is under tensile stresses. We call this anticlastic curvature because if you look at it, the plane on the bottom, one side of this plane is under compression, the other side of this plane is under tension. So that's why we call anticlastic, because they are opposite to each other. Okay? And if you have a piece of rubber which is a bit thick. If you bend it, you will see this phenomenon happening. You will see that this fiber goes under compression and this goes under tension. You can actually see it. So we call this curvature R divided by mu. Mu, of course, is the Poisson ratio, and this is anticlastic curvature, right? So that was the first question or second question that we were supposed to answer. Now, as we continue our loading, what do I mean by that? I mean that increase the bending moment. If we increase M and reach the yield value for the moment, in other words, we increase the moment to a value my, so that the outermost fibers in the beam yield. Okay, so we call that incipient yielding. The bending moment increases to a degree that the outermost fibers start to yield. So as you can see, I have made this red color. It's showing that the outermost fibers have yielded. Okay, so that's what's happening here. Now, as we increase further, okay, we increase the load further, we increase bending moment from my. So this M is greater than my. What happens is that this yielding, which had happened at the outermost fibers, progresses inwards from here towards there like that, and from here towards there like that. So this is what happens to the plastic part. So at the beginning of the yielding, incipient yielding, only the outermost fibers were yielded, but now it flows inward. In fact, the plastic region of the material progresses inward like this. Okay, you can see this 45. In fact, if you take a section and take it under microscope and examine it, you will see 45-degree slip bands. These slip bands are due to the slip planes that have happened and make the material plastic. Okay, plastic deformation we have explained before, that happens in this way. Now these 45 degrees, of course, are for mild steel. If the material of this beam is mild steel, then you will see these 45-degree slip bands, which we showed that for ductile material this is true. Okay, so as we increase further this bending moment, these plastic regions move towards the center line, which is the neutral axis. And that's what happened. The bending moments have increased further, and plastic region has grown from the top and bottom surfaces. The elastic region is bounded between the two plastic regions. So we have these plastic regions here, and this white one is the elastic region, which is bounded between these two. So if we unload it now, we have plastic region here and plastic region here, and some elastic region in between, which is bounded by these two. So this MEP that we have put here, because this moment causes the bending and causes some plastic deformation and some elastic deformation. So that's why we say elastic plastic, MEP, elastic plastic bending. Now in here we have increased MP to such a degree that the beam has completely yielded, and it's completely plastic all over the place. Of course, it's not. This is a perfect situation. In a real physical situation, we don't have all the material. I mean, not all the material becomes plastic, but some elastic parts are in between the plastic parts. But for the sake of argument, we say that as we increase this MEP, we reach a situation where this moment reaches a value MP, which makes all the material plastic. Okay, fully developed. It means it's a fully plastic. Now this is the cross-sectional area. That's the original cross-sectional area. We say that the depth is h and the width is b, and that's the neutral line or the neutral surface or the neutral plane. Okay, we are looking at the beam from its cross-section, and we want to know what are the stresses. Now the maximum stress obviously is mh over 2I, because it happens at the top and bottom of the beam. So that's what happens for the maximum stress. Okay, at the top and bottom. The stress on the neutral surface is 0. Why is it 0? Because here is positive and here is negative. So we are, and you can see that is the distribution of stress. For instance, here the stress decreases until it reaches 0, then it changes sign. So you can see that when we move from the top to bottom, for instance, we have here sigma maximum, which is the maximum tensile stress, and then we know that the maximum tensile stress happens at the top of the cross section. So as we move down, it must decrease. So that is the linear, because it's elastic, that's why it's linear. And as we go down, it decreases. Okay. Now here is the maximum also, but a minus sign, a compressive. Also, as we go towards the neutral surface here, it decreases. Okay. So when we move from top to bottom, it changes from positive to negative. So there must be some point which is 0, and that is on the neutral surface. It decreases, and that decreases. They reach a common point, and this common point, in fact, both of them are the same. Sigma is equal to 0 for the top and bottom, because they coincide in here with each other. Okay. As we increase bending moment, as we increase m, okay, as we increase m, this sigma increases. Okay, this sigma increases, and we reach a point when this sigma reaches the yield value. So that is the ultimate point in the elastic part of the material. Okay, so if we take the load off, if we take this m off, then it will go back to 0. Okay, it will be 0 all over the place. But if we increase m further, then we go into the plastic region. Okay, we go into the plastic region, and here we have shown it according to a stress-strain law, but here we have shown this just elastic and perfectly plastic. Okay, maybe in here I should have shown this. Y is here, not there. Okay, I should correct this. For this curve, y is here, minus y is here, from there to there, and minus plus y also from there to there, not to the here. Okay, but here, because we have this rigid plastic, once we reach this value, it remains the same. So stresses here are all the same, equal to y, because it's elastic, that's elastic, rigid plastic. And this is just a rigid plastic, no elastic. Okay, we have omitted the elastic part. We have considered that this material is a rigid plastic material. So as you can see in here, it's completely plastic all over the place. Now here we have some basic equations for the stress strains. Of course, stress we obtained it in the strengths of material, so I won't go over it. But for the strain, I would like to have a look at it here. Again, you had this in the strengths of material as well, but we are just going to review it at the beginning. So we have some bending moments, and this beam bends like this, and this blue line is the neutral axis, so that R is the radius of curvature of the neutral axis, and that theta is the angle subtended by this part of the beam. This is just part of the beam. And if you look at a fiber like that, this green fiber here, distance y from the neutral axis, then we can write for the strain, that's the strain, elastic strain, delta L over L, or L1 minus L0 divided L0, so it's L1 to L0 minus 1. That's the elastic strain. You see this one which is on the top is under tensile stress, and this is the original line. Okay, when this beam was not under the load, under the bending moment load, all these lines, green line, blue line, this one, that one, all of them were the same, and they were equal to the original length, L0. But now only the blue line is equal to L0. All other lines or other fibers have changed lengths. The fibers on the top have increased their lengths, the fibers on the bottom have decreased their lengths. So this green line which is on the top has an increased length, which we call it L1. So L1 minus L0 divided by L0 is the strain, elastic strain for this green fiber. Now, from this geometry, we said that blue fiber remains neither extends nor shortens, so it is equal to the original length. So the original length is equal to r theta, because in this geometry that we have shown, r times theta is equal to L0. Okay, and L1 is equal to r plus y times theta, because the radius of this green part, is r plus y, and times theta gives us that arc. So L1 is the length of that arc, and r plus y times theta becomes equal to L1. That's the difference here. So we can use these relationships here, r plus y times theta divided by r theta minus 1 here, there, and we get, if we simplify that, we get the elastic strain is equal to y over r. So you can see here that as we move away from the neutral axis, this y becomes greater and the strain becomes greater. So when we reach at the top, we get the maximum strain, which is correct. Maximum strain related to maximum stress. Yeah. Similar reasoning could be given for a fiber, for instance, somewhere here. Okay, for a fiber somewhere here, we can use a similar reasoning like that, and that we could use this to reason for the fiber on the bottom. Okay.